Hey everyone. In this video, I'm going to talk about incrementality testing. So you must have heard about incrementality testing quite a bit now. People are talking about it on the internet. Different influencers are talking about incrementality. A lot of marketing measurement companies are talking about it, and I think it completely makes sense because you have to basically test whether or not any channel or any particular marketing initiative, any strategy is being incremental or not. And by that means, where do you really put in the next dollar that is actually going to give you a return, and to what extent, which you would not have got without that uh, effort or initiative. On the flip side, if you are probably spending money on a channel or a campaign initiative that is not giving you any incremental returns, a good example perhaps is a branded search campaign on Google Ads. So if you're doing that and it's not giving you any incremental returns, why even waste money on that, right? You would have rather invested in something that would actually give you incremental returns. So in this video, I'm going to talk about a specific kind of incrementality testing method, which is called difference in difference. And we're going to talk about two close variants or cousins of difference in difference, or DID as it's called in short, its acronym: the two-way fixed effects, or TWFE, or the even study model. So all these three are very closely related. We are going to see how they are related and in what situation which one you should be using. But let's actually study with a simulated case. Okay, so this is an ideal case where you have the assumptions or the requirements of the model being satisfied. And the most important assumption of this model of event study analysis is the parallel trends. But before going into that, also, let me actually explain what is event. So I have been talking about this a couple of times already online, and I've been getting a few questions around it. So event study, like I said, is very close related to difference in difference. This simply means that you're going to try to understand the effect of a marketing campaign or an initiative by taking the difference between the test and the control. So you're going to apply it on a test, right? So suppose you are testing a new kind of campaign, or testing a new offer, or launching a new product. So suppose you want to analyze the difference, and you want to basically check whether or not that has incremental impact. You might do it in one market, and or maybe a few markets, and then not to do it in a few other markets, and then use them as controls, right? So you basically have the test and control binary. Now you have to take a difference between the pre-test and the post-period differences between these two. Essentially, that's pretty much difference in differences, right? So I'm going to show that to you in a moment as well. In fact, I can just scroll down and show you. There's going to be quite a bit of math here, but this is the basic relationship. Okay, so treated post minus treated pre minus control post minus control pre, right? So that's not very difficult. So it's the difference between the treated and the control, or the test and the control, for the post and pre periods. Post and pre simply means that you are taking, if you look at this diagram, for instance, this zero point 0, that is your intervention point, right? So that dotted line gives you your intervention, and pre and post simply means the period prior to that intervention, and the post means the prior, after the intervention. So you see that one of the important assumptions of, or sort of requirements for using this model, is that you have to choose your controls in a way which should be very similar in terms of its distribution, or in terms of. So first of all, you have to choose a metric, right? So suppose you are choosing revenue, right? So suppose you're applying this on say a market like, say, UK, right? And you have a multi-market model, multi-market business rather, where you are selling the product in UK, in other countries of Europe, maybe Belgium and France, or maybe Switzerland, whatever, wherever else you are selling it. So suppose you are choosing to sort of launch that product or that specific campaign in UK, and you want to have controls in, suppose, a few other countries like, say, Belgium and France, and suppose Netherlands. Now if you do that, so an important, and in order for you to in order for this to actually work, the distribution has to be very similar in terms of sales. Again, by distribution it doesn't, and by similarity it doesn't necessarily mean that they are of equal magnitude, but they should be parallel, more or less, meaning that they should rise and fall at similar levels. during different time periods. So that's basically what the parallel time or the parallel trends assumption means in a nutshell. Kind of oversimplifying it a bit, but in a sense that's what it means. So what you're seeing in front of you, you can see that there are not multiple markets here. Like you would have probably might have guessed, a good question here is that why is there only one graph, right? So we are talking about control and test, but in this case, this kind of a graph is not showing you the counterfactual and stuff like that. What this is simply showing you is the net effect size, uh, in the periods relative to the treatment in the pre and the post period. Okay, so that's what it's essentially showing. And you can see that this effect size is basically the difference. Okay, so you can see that between the control and the test, on an average, in the pre-period, the pre-test period, there was not too much of a difference in effect sizes, but in the post period the effect size difference was significant, and that is exactly what you want. Meaning that at this point, that 0.0, the dashed line that goes vertically, that gives you that intervention point. So prior to that, there was nothing, that there was no impact of that treatment, right? And post that treatment, you obviously have a significant effect, right? So the effect size has sort of grown almost linearly. So, if we were to talk a little bit now about what is the mathematical formulation of this is the event study model. So, again, just to sort of give a context, like suppose you want to, so we are entering Q4 now, right? I mean, this is a very important time of the year for e-commerce businesses and anybody who's selling stuff online, and you know that this is the time when people are going to come and buy in bulk, and they're probably, a lot of them are simply holding off and waiting for Black Friday to arrive to really make big amount of purchases. So this is the time of the year where you want to also, now, I mean, not around Black Friday, but earlier than that, like suppose around September. In fact, you should have probably already done this by now. So yeah, I'll apologize for that, because I probably should have released this video earlier, but yeah, better now than never. So the idea is that you do tests now, so that you know that what things do work, and they simply will be working at a larger scale. So during Black Friday, that's the idea. So you get the tests done now, you figure out what's working and what's going to work then. Okay, it's not 100% foolproof, of course, because what might work then may be a little bit different than what's going to work now, but at least it's just a few months away. So yeah, you get the drift. So this is the mathematical formulation of it in order to do the event study model for incrementality testing. This theta here, that actually represents your so there are two kinds of effects that we're going to look at. Okay, so you must have heard that I'm using the word effect quite a few times. So we're going to use two kinds of effects. One is called the unit effect, or the unit fixed effect. The FE stands for fixed effects, and that's your eta here, this symbol looking like n, and this theta is your time effect. So there are two kinds of fixed effects that we're looking for. So what do they really mean? These mean that you are trying to absorb this regression that you're going to do, right? This equation obviously has been written in this format, as you can understand. It's only to carry out a linear regression on them, is to absorb these two effects. Okay, and what that means is the the in time invariant differences across units. Okay, so for instance, UK always being larger than Belgium. All right, so these things will also have an impact, right? So suppose when you're doing this event study plot, you only want to figure out or isolate the impact of your treatment of that campaign. By treatment, again, these are terms which are common in statistical parlance, and just don't bother about that. The important point is to understand the essence of it. So you want to only understand the impact of your campaign, of your marketing initiative, and not let your model get drifted, or not get results which get distracted by, or sort of influenced by other factors. So that's why you want to control for them in your regression, and that's why you have included this fixed effects, as I was just showing here, which is the unit fixed effect and the unit time effect. So there may be variances also across time, right? So there can be seasonality or holidays, right, or macroeconomic factors. So you want to control for time factors, you want to control for geographic differences. Once you have evened those things out, now you're on a playing field, right? Now, so now it's in the pre and post period, the only thing that's separating these units is the treatment that you have given. So that's basically the whole concept of incrementality testing. By the way, I'll be sharing this Notion doc in the description of the video. So yeah, nothing to worry. So the next part is this summation. This complex looking thing is nothing but a summation of different time lags, or as they're called, event times. I'm coming to that in a moment. And this DL gives you essentially the treatment effect, on whether or not it's going to get treatment rather, and mu L is going to give you the treatment effect. Okay. And then you obviously have V of IT, which is going to stand uh, for your errors. So let's actually look at, so as you can see, this is the error term, but let's start with the event time dummies. So the event time is nothing but the difference, that lag basically, between the time at which you're observing, the observation time, and the time at which the treatment started. So for instance, um, L here, lag, is given by T minus capital T of I. Okay. And for example, L equal to -2 means that 2 periods before the launch in that unit, and L3 means 3 periods after. Okay. So for instance, if I look at that graph again, L0 simply means that it's actually at that, at the time period of start itself. So it coincides with the starting period when the treatment started, right? So that's there is no lag. But if it was suppose at -2.5, this would mean that it's, L would be -2.5, because it has started at times t0. So that's basically your event time. That's how the um, that's how DL is defined. So DL then becomes 1 whenever it's going to be in the format L minus T. Okay. uh, I'm sorry, whenever it's going to be in the format T minus T, which is equal to L. All right. So this is 1 in that case. And then you have also the fact that it's getting treated at some point. So it has two parts of it. First of all, it has to be a treated unit. If it is not a treated unit, so not all units, so you will have multiple units, right? So in your data set you can have, and by units again I mean, it can be geographies, it can be markets, it can be products, right? So depending on how you're formulating whatever is your unit of testing basically. So the example I gave is maybe of a product, it could be geographies, I mean, but yeah, if it's a geography then it's confusing. So it has to be, because you're testing it across geographies as well. So you should be deciding how you want to decide. So in this case, for instance, it was geography only, right? So you can decide how you want to, what is going to be the basis of analysis. So it has to be treated. So if it's not even getting treatment, that unit is not even part of the test, then obviously it becomes 0, and this becomes, so as you can see, for controls it becomes 0, but for treated units it actually becomes equal to 1 at each time point t, right? Because there is a certain lag. And your so that's, the mu L is the incremental effect at that time, at event time L. This is something that again is depending on how much the effect is really in the model. And that's basically what it's going to try to understand, right? So that's what it's going to try and isolate after the analysis. What is the effect at that particular time, um, you know you know at that particular, on that particular unit. So that's why it's called a two-way fixed effect, or a TWFE model, because you're taking the impact of both time variation as well as unit level variation. So if I actually now go back to the, you know so yeah, if I actually go back to the main formulation of this model. So this is the formulation again. So this one is the formulation for the model, where you have the unit effects for time and units, and you also have the combined effect, where you are getting the, whether or not it's getting a treatment, and then the value of the treatment itself. So that's how it is getting different, getting defined in here. So hope that makes sense. L, like I said, it's going to be 0 for the period when it starts. It's going to be greater than 0 when the treatment is already over, and then pre-treatment periods is basically your L less than 0. So there's a bunch of stuff here as well, how you can actually get started with it. I'm actually going to show you an example from from a code itself. but I'm going to jump into that in a second. In the meantime, I'll show you also a couple of other things. Like for instance, if you want to figure out the average treatment effect on the treated, so this is how you can do that. Like you just take you just take the summation of the treatment values, which is, or the treatment effects, which is mu of L, and then you divide it by an absolute value of the different weights. Okay, so once you do that, that's when you get the average treatment lift per period. So sorry, this is not really weights, this is actually weeks. So this is the window, rather, you can say. So so if you're trying to get the lift per period, you simply have to divide it by weeks, or the periods, rather, that window. So that's the average treatment effect, in that definition. As per that definition, the other thing that you should be looking at is the basic DID model. So we have talked about the generalized version of the DID, or the DIDs. Like I already mentioned, this is basically the concept, but the regression format looks like this. So similarly, you can see here there is a similarity in the concept, where you have a treatment effect, where you have a where you have a time effect, where you have a the post is basically the time effect. So this again is binary, like whether it's 1 or 0, and this again is whether or not it has gotten the treatment, right? So whether or not it's in the treatment of the pre or the post period, whether or not it's gotten treatment, again 0 and 1, and then you have a combined variable here. So that's how DID works. So this interaction term, whether or not it's getting treatment and whether or not it's in the post period, that's what matters, right? So that beta 3 is actually the DID effect, as you can see, that coefficient. So this is very similar to 2W, the two-way fixed effect. And as you can see that it's actually a generalized form, right? So that panel data that you got, this is basically a generalized form of DID itself, right? So you have one dummy per unit, which is gamma I, one dummy per time variable, which is lambda here, and that treatment status only on a treatment unit, which is in post. So you can see that you can rewrite from this expression. If you also read through this section here, I've already explained it, but if you want to, you can actually understand why basic DID is nothing but a special case of TWFE, okay, which is a two-way fixed effect. Um, if you want to understand also why this equivalence holds, so the classic DID estimator is based on difference of differences calculation from the mean outcomes of different groups, right? And these are the, a different combination of treatment and whether or not it's a control, or post, whether or not it's in the pre or post, or whether or not it's treated. And then the two-way fixed effect is just regression for the 2 into 2 case, includes fixed effects for the two time periods and the two groups, right? So therefore it's and plus an interaction term. So therefore, like I mentioned, the two-way fixed effect becomes just nothing but a specialized case of the or rather a general case, and the DID a specialized case of the two-way fixed effect. But there are certain situations when this does not work. This equivalence is becomes more complex, because there can be multiple time periods where the TWFE estimator is no longer the same as a single DID calculation. But again, in principle, it remains same. Where it becomes a bit more complicated is when there is staggered treatment adoption, right? So different units may actually have may start getting treatment at different time periods. So that's when it also becomes a little more complicated. There may be also heterogeneous treatment effects, right? Where the treatment is actually not constant. So this is also very useful, where suppose if you have started a marketing campaign, and the not only are the different units starting at different points, like for different geographies, the campaign is starting at different times, which makes it staggered, but they're also getting different amounts of treatment. Okay, by treatment again means that how much you're spending in different geographies. So suppose you're starting the campaign in different geographies, but you're also spending different amounts. So that becomes a very complex, it becomes staggered in both time and space, in units. So that then becomes a more complex version of this two-way fixed effects model. So essentially, however, the idea is event study, and you can see that there's a hierarchy, right? So the simple DID is the foundation. TW fixed effects is a regression based generalization of DID, when you apply it to multi-group or multi-period panels. and even studies an extension of TWFE that allows treatment effects to vary by time relative to adoption. Okay, so that's basically your hierarchy, and it's important to understand the fundamentals. Now I actually go to the quickly to the case study. This is a simulated case where you basically have different time periods, and you have different units, and you also have the starting period for the treatment for each unit. So if I just go to the explanation of it, I'm not showing you the code. That's going to unnecessarily look complicated, but this is the output table of that, and this is the average treatment effect. So you can see that this is actually a raw panel data, a raw simulated data, and ID is the unit identifier, the different units. Like I said, this is the period in the calendar, the time period, and then you have the first treated period, like I said. So if it's G equal to 7, then that unit got treatment at, it started at the period 7, and this is a simulated outcome for different units and at different times. So unit fixed effect, time fixed effect, treatment effect, and random noise, these are getting summed up to give you the ultimate simulated outcome. So the unit fixed effect and the time fixed effect, like I've already mentioned, they actually give you the regression model which is controlling for these essentially. So the shocks and the differences which are coming because of this individual fixed effects, they are getting absorbed because you don't want them to influence your understanding of incremental effect. Now comes another part where you have actually created what's called the event dummy. So remember we were talking about this D here. If you go back to this code, this DL DIT of L, this basically gives you the different time dummies, right? So this is depending on the lag, and based on that, what we have done is we have created this particular table now. So this basically gives you, suppose if I look at this explanation here, so at time period 4, even time is nothing but L4 minus 7. Remember we said that it starts at 7. So for instance, in this case, if it starts at 7, right, so this becomes D minimum becomes 3. So by the way, these 4 have been defined. So D minimum 3, D minimum 2, uh, these two are lags, and these are the leads essentially. uh, you know these are the 5 periods which have been defined as, which we are really concerned about: periods before and after, okay, the treatment. So there are 2 periods before the treatment and 3 periods after the treatment. So and obviously, uh, time t equal to 0 is the period when the treatment has been given. So at time 4 the lag is minus 3. So there is the value, as we know, as we have already discussed from that model we showed earlier, that that event study model, that D minimum 3 is going to be 1, right? In fact, as you can see, in each of these cases it's always going to be 1. Only in these cases, by the way, nothing in at no other point. So only for these periods from 4 to 9 are we going to get any values at period 6. So that's basically your L equal to minus 1. Now this is an interesting thing. So where do we do the baseline for models? Okay, so if I actually show you, I'll show you I'll talk about the OLS a little bit in a second, but if I show you the plot first, of the way this has been done here, you'll see that the plot here has been done at minus 1. I've deliberately kept this different. In this example, the one I showed in the note in the Notion document, the baseline here is zero point 0. So that the baseline here is the same as the treatment period, or the time period at which the treatment was given. In this case, it's L equal to minus 1. The time period is still the same, right? The time period, in both cases is the same, which is 0. But in this case, the baseline has been taken as minus 1. And this has been normalized artificially as 0. Okay, in this case, it was normalized artificially at 0. This has been artificially normalized at equal to 1, L equal to minus 1. Remember, this is not time period, this is event time. Event time we have defined as lags. So do remember that this is T minus T, capital T minus or small t minus capital T I, which is the time you're observing now, minus the time period at which it got started, right? So that's how this calculation has been done, as you can see here. So there is actually an advantage of doing this, and the advantage is that you are basically, it is intuitively going to make more sense if you actually do the comparison for each period's effects. So essentially what you're trying to do is you're trying to understand the effect relative to this baseline, right? So that actually makes sense. Like, you want to compare it with the period, the most immediate period before the treatment effect, right? You don't want to go too far into the past. You certainly don't want to compare with the period which has already got a treatment. You want to compare it with a period which did not get a treatment, right? But that should also be the most nearest one, which is why L minus 1. At the same time, you might wonder, why not L equal to 0? Because at that point it did not receive any treatment. And so at that point the treatment has already been given, right? So it has already got the treatment, so it's not a very good baseline to compare with. So that becomes your cutoff point to separate your pre and post, but it's not a great point to do the analysis with, the comparison with, if that makes sense. Okay, so I know this sounds a little confusing at start, even I was, as to why the baseline was 1, but this is how it's done. By the way, an important point here is that there can be multicollinearity when you're doing this kind of dummy variable analysis. So I'm going to come to that OLS point now. So so hope this up to this point was clear, that we got all the dummy variables. This is what gives us this kind of a table. You understand why the different ones are coming, right? So the one is only coming in those situations, right? So for only those situations that the value is going to be there where it actually satisfies our condition, right? It's one for the condition of t minus t, and it's going to be giving us important values only for those periods which we have defined, right? Which we are focused on, which is 3 periods prior and 4 and 2 later. Or I think, no, sorry, it was the other way around: 2 periods in the past and 3 after. For all other periods it will only give us zeros. And you can actually see that's always the case, right? So that's why you see that it's only showing for 0 to 9. For all other periods, you're not going to get any of these values. It's only other values which we don't really care about, right? So now we are going to talk about the regression. So after this, you basically construct a regression equation, and I'm going to show you the nature of the regression equation. You can see the output here consists of intercept, consists of all the different variables, right? So you'll see that so basically in this example we had 200 units, okay, and 12 time periods. And what we have done is, what this output naturally gives, like any regression output, it gives you all the different intercepts, I'm sorry, all the different variables and their coefficients, essentially. Okay, the coefficient, the standard error, the z-score, and the p-value, and the interval. But we are only concerned about a few of those, and we are only concerned about these few ones here, right? We talked about the 2 before in the lags, and the 3 in the lead, right? So these are the only ones we are concerned about. The rest we are not concerned about. So what I've done is, in a later code as well, what I've given is only these parts. So these parts are actually going to match exactly these part here. So it has only truncated the output to this part. So you can basically take a look at that as well. These are coefficients and these are your standard errors, right? And you can also look at p-value and z-score and all. So obviously this is a synthetic data set, and you will see that pretty much for most of the values you will have a statistically significant value. Okay, so you'll see that these are not statistically significant though, in the dmin and dmin 3 and dmin 2. So that's actually not statistically significant because it's far more than 0.05. So yeah, anyway, so this is what the regression really looks like. So dmin 3 plus dmin 2 plus dt3. So these are your unit so these are your unit effects, right? Which are based on your event time lags. And this is your dummy variables, dummy coefficients for unit fixed effects. These are your unit fixed effects. So event time dummies are given by these, and each measures the average effect of L. Okay, average effect at L at different time lags. So -3 and -2 and 0, 1 and 2. Okay, so that's how it's given. So this corresponds, these two here, CID and C period, these two correspond to your eta and your theta. Remember we talked about the unit time and the unit fixed effect and the time fixed effects. So that's basically the output. And we go on to then plot the output, this is how it looks like. Okay, so again, what this means is that you do get a change after the treatment. You do see that the net effect, the difference between the control and the test, is there appearing at different time periods, and you can see that it gives you an idea of persistence or decay, right? So the effect doesn't stay constant. So you can actually see, so what you're measuring here is the direct effect, and the direct impact, incremental impact at different time lags. And at different time lags the effect is actually varying. So this is a very useful thing. So you know then that, okay, if I go into, suppose Black Friday becomes your baseline period, right? So just think of it theoretically. Just imagine at zero is your Black Friday. If this is your effect, and if you trust this output to actually work also in that period, like I said, there's going to be a good reason to trust. If you have taken into account all important factors in this model, then you can see, then you can sort of interpret this as Black Friday being at point zero. You can expect it to drop a little bit after a couple of periods, and you can also think of it as some other way as well, like what's going to happen in the past, and so on and so forth. So depending on at what point you're imagining in the future as your key event, what's going to happen prior to that and later to that, this is something that you can sort of analyze or interpret from the event study model. So these are called dynamic treatment effects, by the way. The analysis that we did on dynamic treatment effects mean that, like I mentioned with the example of the event study plot, that you can have staggered uh, treatments at different time periods, so therefore different units get treatment. Or suppose you have different markets, right? So I said that you want to compare it with with UK and Belgium and France, compare among these markets. Suppose these markets get that campaign at different, the campaign starting point is at different dates for each of these markets. That is your staggered version. And then on top of that, you also have, suppose the effect size becomes different, like you spend different amounts in different markets. So that is basically ideally captured by something like a full-fledged event study model, where you are using the dynamic effects concept. So hope this was useful. I know this is quite a bit. This is, by the way, very strongly influenced by this paper here. It's in a github.io by Brantley Callaway and Pedro Santana. In this was released in 10th September of the last year. And you can see that very similar, that precisely that equation has been given, and the code here is the R code. And again, a very similar graph. So I've basically given the Python version of it, because I'm far more a Python person than an R person. So that's what I've worked with here. And if you have any questions, I know this is quite a mouthful, but event study model is being used by quite a few people out there. You might have seen in Common Thread Collective, in their software Statlers, they're actually using event study model there as well. So if you want to truly understand incrementality testing, you will have to dive into causal inference methods. That's one term I did not use in this entire video, but it is basically a kind of causal inference method. It's going to give you the causal impact of the intervention of the treatment that you're trying to analyze here. And there are other causal inference methods, of course, but I spoke about the most important ones, like DiD, or difference in difference, and its close cousins or its close variants, two fixed effects, and your your two fixed effects, and your event study model. So essentially, it's an event study model. So these two are just close variants of it. So hope this was useful, and if you have any questions, do let me know in the comments. And as always, I'm totally happy to answer any queries that you might have, or if you need any kind of assistance. But that's it for now, and thanks for watching. I'll see you in the next video.